Good afternoon and welcome to today's webinar on quality assurance and quality control. We are in the 7th session of our 8-part series, and we will be hearing from Forrest Breyfogle again, but I would like to go over the standard housekeeping as usual. This is about an hour. It may be a little bit shorter. We like to leave time for questions, so please be sure to enter those in the text box of the GoToWebinar service. So as the webinar is progressing and then again at the end, we like to take all the questions. We will be recording this, so we'll send you the email as usual so that you can access the recording as well as a copy of the slides. So now I will turn it over to Forrest Breyfogle, who you heard from last week, and we will get started. Thank you.
Number 7 in the 8-part series. Okay, before we get started here, let's go in and look at this question here. Which statement best describes you? So please respond to the question. None, rarely, some, or frequently. Okay, we got about 50% has voted here. Okay, let's go in and close the polls here and see what we got. Okay, so it looks like frequently and some has run as a tie. Okay, great. Well, appreciate for your response for that. Thank you. It gives you a little idea who's out there. So these are the learning objectives we're going to be covering in this particular module. We're going to be looking at the difference between the quality assurance and the quality control. And we've talked previously about the project to make tools, either basically overall roadmap. But again, a lot of those tools are applicable to both quality assurance and quality control. And that's what we're going to really be talking about this time. So what do we have when we mean quality control? Well, it's get involved in the testing of the products, or sometimes we have transactions where we're really looking at defects in order to make sure that we meet the customer's requirements. Now, these customer requirements can be both product requirements or it can be the company itself. So that's basically what we think about when we talk about quality control. Now, when we get into quality assurance, we're looking at testing of products to improve or at least to minimize the issues that we might have relative to defects or in both productions and whenever we're processing transactions. So that's kind of the difference between the two of them, at least the way we're going to look at it in this session. Well, before we get started here, we got to look at what we have relative to measurements. And basically, there's 3 different types of measurements. Now, the first type is dealing with product quality. So let's say you make a widget, and you want to say if that widget is good or bad. And it's got a certain tolerance to a dimension on that widget. And we go in and say, hey, this part is good or bad. So we're not really drawing conclusions about the overall process that made widgets, but we're making a decision on whether that widget is good or bad. That is, it's within or outside the specification. So when we do that, that's part quality. And we can consider that to be a quality control type usage. Now, we have another situation where we receive a batch of widgets. And we want to make a decision whether these batches of widgets are considered good or not so good. And when we do that, or when we make that evaluation, we typically draw a sample. And then from that sample, we make a decision relative to the overall performance of how that batch, at least we believe, is performing relative to what we need. So that's batch quality. So again, this is a quality control opportunity here, or quality control application. Now, if we look at process capability, that's another way we can have a measurement. That's the third of the 3. Now, in this case, we're looking at an analytical measurement where we're assessing the process or the product measurements to establish how the process is going relative to its stability and, as we talked about previously, its predictability to the future. And we can make a statement of how it's actually performing. So we might say the process is performing at an approximate 3% defective rate. So that's basically what we might have when we're looking at a quality assurance usage. So again, quality control is about verifying the product or the transaction, whether it meets our particular requirement. Now, when we're looking at our P2Make tools, one of the tools that kind of jumps out at us is a measurement system analysis. So the idea, we can get a measurement all right, but it may not do a very good job relative to what we're trying to measure. So for example, if we've got a yardstick and we're trying to get a diameter on a shaft that's a tight tolerance shaft, that's not a very good measurement tool to get and make a decision whether that part is good or bad. So that would not have a very good measurement study on it. Now, as part of this overall project to make tools, we also have the capability analysis. You know, we're big on probability plots when we can use them for not only tests of normality as we described previous sessions, but we can also use those to describe the capability of the process.
We just received some feedback that there's some difficulty hearing Forrest, so we're going to try this method, so please let us know if you get any other difficulties with the audio and we'll adjust accordingly.
Okay. So what we've got here is probability plots and the capability analysis. Now, when we're talking about capability analysis, we're not really big on using the CP and the CPK and PP and PPK to describe how our process is performing relative to the capability or its performance metrics. As we've described previously, sometimes this is speaking a language that people don't often understand. We'd rather go in, if we got a specification, translate that to a long-term defective rate. Another thing that's often used in quality control is acceptable quality level type of inspection. This number, as we're going to be talking about a little bit later, it can be very deceiving, and so we don't recommend using that either. Okay, when we're looking at the overall measurement analysis, we've got an observed measurement. Now, this could even be in a doctor's office where we're looking at your blood pressure, you know. So it's not just measuring the widgets. They may even go in and be in the judicial system. Is a person innocent or not? They're truly committed to crime or not, but do we have a good gauge on how we determine whether that person is innocent or not? So a lot of times we don't think about how gauge R&R and measurement system analysis is applicable to a lot of things that we often run into during life. But in reality, there's a true value. But in reality, we don't know what that true value is. We just got an observed value. So there's a component of that that's we call measurement error. Now, if we break down measurement error, we can look at it 4 different components: gauge R&R, stability, bias, and linearity. And then gauge R&R has 2 particular components of that, repeatability and reproducibility. So we're going to talk a little bit about each one of these. So repeatability is a variation of measurements given that the same part within the same operator. So we've got a particular a widget that we're measuring the overall dimension on, and we want to see if that person gets the same number when they examine that part over and over again. So you would like to believe that they do, but they don't necessarily do that. Now this can apply also in if you're doing a lean event. How long does it take for something to occur too? So if somebody looks at it again, if they could go back in time, would they actually get the same number or not? So we want to look at the characteristic that you're measuring, and also we look at different operators could have different repeatability. So one person may be very consistent on how they measure a dimension and get the same answer, right or wrong. Somebody else may be very inconsistent on how they get that particular answer. Now, in our black belt training, we use a catapult. We use the plastic golf balls, and the question is, does our measurement for the distance that the catapult shoots the ball, is it repeatable in its measurements? Now, we could say, well, yes, but could have inspector fatigue, or we might say, hey, there could be a difference in viewing angle. So all these things could affect the repeatability that we have. So somebody might move their head a little bit, they could go back in time and not get the same answer. So it has probably some issues relative to repeatability. Let's look at reproducibility. Now in this case here, we want to use the same gauge, and we're looking at the same identical characteristics on the part. So maybe it's a diameter that we're looking at. Now in this case, we want to compare the operators. Now the question is, does the catapult process have a lack of reproducibility in its measurements? Well, it really does. We could have, the operators could have different viewing angles to throw, different definitions for where the ball hits. I was just observing a shooting the other day, and I was convinced that they were off by a couple inches. It was just a visual inspection. But, you know, and that's can have very different opinion on how the shot distances is. So we've got to keep in mind that this is very applicable to a lot of things that we might encounter. If somebody else was going to take your blood pressure, would they get the same answer as another person? Because a lot of our diagnostics is based upon how we go in and get those measurements. Or say you got a blood test. You know, you had two different people making some sort of a measurement on it. Do they get the same answer or not? You know, because a lot of times they'll look at a specification on a blood test that you might have for a physical, and if it misses it by just a little bit, then you'll say, well, you got maybe an issue here. If it's within spec, then they don't say much about that. But you can have issues both ways because of this kind of a problem. Another kind of quality control issue you can have is instability, or it can be drifting. So sometimes things change over time, and that can really make a big difference. Monitoring through a control chart or master chart can address that. We might have even the gauge could have some sort of a drift to it. Measurement system is stable if its mean does not fluctuate over time. You know, and that's how we could test that. So if one way of looking to see if our gauge needs calibration, we could take a golden part and measure that particular part over time. And if we did on a control chart, it should have just some up and down movements and have no trends to that. So that's one way of observing to see if we have some instability relative to the gauge that we're using anyway. Another way we could have some issues is bias. You know, bias is a difference between the actual value and the true value. So if we've got a micrometer and we're measuring a dimension on a part, it might be off by 1/1000th of an inch. And so therefore, somebody could be measuring it and get 1/1000th of an inch larger than that. And then a linearity is if we used a micrometer that's a 1 inch, and then we go in and measure something that's very small relative to that 1 inch micrometer, maybe an 1/8 of an inch diameter part, it may respond differently than if we were measuring a part that was 0.9 inches. So that would be maybe a linearity issue in that particular micrometer. Now, what about the catapult again? Well, we can maybe have some difference depending upon how far you throw relative to our measurement system that we have, especially if it's visual. If somebody starts shooting it farther, all of a sudden that could change the angle of how you're looking at it. Now the question is, do you think that these tools, or these issues, I guess would be a better word of saying, are applicable in quality control. Say, for example, you've got a part that you're receiving from an offshore supplier. You think that that might make a big difference? Well, it sure can, because we might be saying a part's good when in reality it's bad, or vice versa, because of a measurement system issue. So these tools are really applicable, outside of the projects that we're often faced with on Lean Six Sigma efforts within an organization. So it's important to keep these in mind when we're going to make and pass judgments within parts that we might be using in products that we're making. Now, just getting back to this measurement system analysis issue, if we're looking at the average value, that's dealing with the location. That's dealing with stability, bias, and linearity. So if we're dealing with the supplier, we really want to make sure that we calibrate the gauge, to make sure that we address those issues, because that's where that's important. Now, the other thing we can have that's dealing with the standard deviation is a spread. So in other words, the overall spread that we got relative to the measurement system analysis is the total values is equal to the square of the product standard deviation plus the measurement system standard deviation. And the measurement system really has two different components. The measurement variance, it's got the repeatability variance squared and the reproducibility variance squared. Okay, so if we got a lot of inconsistency on our supplier when they're measuring a part and they're giving us some numbers to that, maybe between operators or within operators, that's going to affect our overall measurement system and our overall view of how the quality control is doing relative to the needs of our specifications that we're asking for. Now, given a little bit of visual that you might have here is how, if we've shown there on the graph below it, we've got an acceptable region. If you're well within the specification and you got some measurement error, it's not too big of an issue. But once you go in and start getting close to specification, you've got a region of uncertainty shown by those distributions near the tolerance here. So if it's really bad, we're confident. If it's really good, we feel pretty good about it. But if it's hovering around the specification, we just really are not too sure, because we can be it can look okay, but in reality, maybe it's not quite as good as we might think it is. Now, one way of expressing the measurement system analysis issue is the precision to tolerance ratio. So we're looking at 6 times the standard deviation divided by the overall tolerance. And then that's one way of presenting it. So in this case, we're showing here a 22% value. So in other words, the 2 represents the 6 times the standard deviation, and the overall tolerance representing is 9 units. So we get 22%. Now, if we're doing a gauge R&R study within Minitab, we've got to be careful on how we're looking at the outputs, because sometimes we can be somewhat fooled, because one of the outputs that Minitab gives you is classification of number of classes that you might have. But we need to be careful on how we view that particular output, because the standard deviation that's used to actually calculate that value is the standard deviation of the particular parts that we have. So if we've got parts that are close to each other, then that standard deviation is real tight, and that gives us one number. But if we've got a lot of variability between the parts that we happen to pick for our gauge R&R study, then we can get quite a different picture. So that's one thing. And also any of the measurements relative to study can be challenges, or can be challenged. So one of the good ways of doing it is, like I'm showing you here, is showing the precision to tolerance ratio. The other one is the precision to the process ratio, and that's another way, that's a good way of looking at it. So just be careful if you have a supplier saying, well, we've got a good gauge R&R. Well, it might be just because they've had the parts when they did the study that were widely different. and then by that nature of it, it might tend to look better than it really is. So just be careful when you're looking at it again. Compare it to the tolerance, and then compare it to the overall process. And when you look at the overall process, where you get that variability from is from the overall variability for a 30,000 foot level chart. Okay, let's move on to capability analysis. There's some complications relative to capability calculations, and so you have to kind of decide what's best for you here, I guess. But there are some really important questions. Are measurements really capable? If we're well within the specification, then we say it's really capable. But the other thing that's really important is the process in control. Is it from a stable process? Because if it's not, then really all bets are off. I've seen more than once that people are going in and not looking relative to the stability of processes, and they're making capability statements. So if your supplier is going in and making capability statements without showing you a control chart that says, hey, that our process is stable, I think that's a big red flag. You need to ask for them both. Also, it's important to keep in mind how the samples are actually collected. If we've got samples that are all from one batch, they're going to tend to look relatively similar. But if we have variability or parts from different batches, then it could be quite a bit different. So we need to be able to be careful on how we get the data. Sometimes when we're verifying a supplier from a quality control point of view, we might ask for a sample of parts that they've got. Well, that may sound good, but the problem you can have is that's not showing typically the variability that they might have from the process over time relative to adjustments changing, raw materials changing, and so on. Also, how much data is used to calculate the capability is important too, because you're going to have a certain amount of confidence interval relative to the capability statements, because typically we have to make statements relative to the tails of distributions. And when we start doing that, we get a lot more uncertainty to it. We've got enough uncertainty, as you know, from the Lean Six Sigma training relative to the means, but when you start looking at the tails of distribution, it can really get wild and crazy. So capability and performance calculations are really dependent upon standard deviation. Mathematically, they're pretty simple. They're just looking at the spread that you have, basically, and divided by the 6 times the tolerance that you have, divided by 6 times the standard deviation. But the question is, where do you get standard deviation? Is it short-term or long-term? So if you're doing an X-bar and R chart, then the standard deviation comes from within subgroups. Well, that's one thing. But what if you're doing an individuals chart and you do it in Minitab? Well, the variabilities come between subgroups. So that can make a wildly different answer relative to what you're reporting to somebody else, or what your supplier could be reporting to you. You know, often when people go in and start looking at the process capability analysis, they're really trying to look at the defective rate. So that's basically what they're interested in. So the question is, why don't you just go in and do that in the first place? Why do you get into these CP and CPKs and PP and PPKs and so on, and as opposed to just going in and why look at CP and CPKs when you can go in and get a number that could be a lot more meaningful to all levels of the organization. Also, the other thing to keep in mind, too, is normality issues. So if you're reporting CP and CPK, PP and PPK, it's very sensitive to things being non-normally distributed. So we can handle that through the probability plots. So this is one thing, is you see it's in bold and red, because this is also a mistake that people make a lot of times, is they estimate capability for unstable processes. You just flat should not do that. If you got regions of stability, the audit can make statements about those. If something is not stable, then you can have issues. Now, as you know, in 30,000 foot level charts, we have a different way of determining if a process is stable or not, because process stability or the determination thereof is dependent upon how you're sampling and how you're viewing the data from your sampling plan and so on. So just determining if it's stable or not is dependent upon how you actually do it. And that's the reason we're big on this 30,000 foot level approach for actually making that sort of statement. Now, we're going to say that this control chart is in control, and it's so we're going to look at this from a region of stability. So if it's we plot it now on a probability plot, then what we can do is put the specifications on that. In this case, 72 to 78. We notice about 14% are below it, and about 4% or so are higher than that, and we end up getting about 17.4% out of specification. Now that's the best estimate. Now you notice that the other two blue lines there that are on the outside of that straight line in the middle, that represents the confidence interval. So you can start seeing how wide your confidence interval could be. You know, typically we report the best estimate, but in reality, don't take that estimate to the third decimal place because you do have a certain amount of uncertainty to that. Now, with the 30,000 foot level approach, I don't really get too concerned about that because if we don't like the answer relative to whether we got 17, 14, or 20, we're going to be working on continuous improvement efforts. So, you know, even though we don't have a precise number, then I think as long as we're working on process improvement, that's kind of the right kind of activity if this metric is important relative to the business as a whole. Now, you notice here we had 17% using the probability plot, and if we were taking that same data and looking at Minitab's process capability analysis, and we look at the lower right-hand corner there, we notice that we got about 173,000 parts per million. So you've got ppm total. You notice that that translates to about 17%. So we get pretty much the same answer if we're doing the probability plot, or we're actually looking at this plot that Minitab has relative to process capability. Okay, we've got another question here. So which statement best describes how your organization is using these tools to assess capability? Looking forward to your responses here. Okay, we got about 50%. Okay, let's close the polls here. Okay, it looks like some. Okay, some is the winner, and frequently and rarely has got 14%. Okay, well, thank you for your help with that. So, again, just to reiterate, I suggest that you don't use this tool CP and CPK and PP and PPK. Again, that can, I always kind of look at this if I were using these kind of terms to describe the process to the line worker and also the CEO, would they really understand what I'm talking about? The answer is typically no. I've had some very bizarre questions asked of me over the years relative to these indices, and what I typically ask them, I'll say, whoever's asking me the question, I'll say, how long have you been working at this? Oh, maybe 3 years, they might respond. And I said, okay, you're confused with this, right? He said, and I said, okay, and I'm not challenging your intelligence here at all, but if you're confused at it, you really are trying to understand these particular indices or having difficulties, how do you think somebody else that doesn't have the desire to understand it as much as you do, how do you think they feel about it? The answer is pretty much that they don't really understand it at all. And now, then if you're going to do it, and you got two-sided spec, another thing is CP and CPK. You got to talk about both numbers. You have to have two numbers really to talk about the number of nonconformance. And people don't even look at that. That's another issue there. They talk about CPK or PPK, and if they got a two-sided spec, they have to be talking about CP or PP at the same time. And just people are missing it. And also, again, it's very dependent upon normality. And how the standard deviation is calculated. Because in CP and CPK, again, just to reiterate, the way you calculate that, if you've got an X bar and R chart, it's within subgroup variability. If it's an individual's chart, it's between subgroup variability. That can make one big difference on that standard deviation in the result that you get. And again, just how the data is collected. If you're doing an X bar and R chart, if you're doing an individual's chart, again, if you're doing an individual's chart, how are you actually going in and subgrouping? What's the time frame between them? That makes a big difference too. So just keep that in mind. So that sometimes your supplier might ask you for that, but can we go in and just give it to the supplier, but we really use some other approaches internally, and maybe we can convince we give it to our customers, excuse me, and but maybe we can eventually convince our customer to actually transition over to the other kind of metrics that we're talking about in this the IEEE approach. Here's another point here that confidence interval. You can see how the confidence interval can get really wild on sample sizes. You got to get like above 40 of them before you get any kind of real spread on it here too. So you can see you got from 30, it's for the confidence interval, if you got a 1.3 CPK, it gets to be less than 1 to well over 1.5. So again, just another point to keep in mind. Now, another thing that I'm suggesting you don't use is AQL. Boy, I'll tell you, this can really be a bag of worms. And people typically don't really understand what they're getting when they're actually signing up to this MIL standard or ANSI standard. Consumers like it, really because it really sounds good. Hey, I got an acceptable quality level of 4. You think you get 4% nonconformance, but in reality it could be a lot higher than that. What you're really doing is protecting the supplier. And if you're a supplier that has integrity that's not the best in the world, what they could often do, unless their shipments are really bad, is just send the same shipment back to them, and then the odds are that it would pass unless it's really bad. Now, I think it's interesting. Sometimes the customer will go in and try to mark the shipment so that they say, well, I want to make sure they don't send the same shipment back. Okay, what does that tell you? That's telling you got a gauge R&R problem with your testing. So AQL, basically, it has a fundamental gauge R&R test. Now, to illustrate that, let's look at this. Well, we've got an AQL of 4%. So we've got a sampling plan. You can go and look in the tables for inspection level 2. It has a sampling plan of 13, where you can accept with 1 and reject with 2. Now, we're going to consider our sample size as small relative to the population, which is really not true. But what we want to do is determine the 95% confidence interval that we might have if one failure occurred. And then we're going to conduct a hypothesis test on the 0.04 failure rate, because that's what we think we're getting when we do the AQL. Okay, when we do this, whoa, look at 1 and 13. The upper bound is 31%. Well, you thought you were getting 4%, but the upper bound for 95% confidence is 31%. My goodness gracious. So in other words, our sample would have to be really bad before we're going to have a good likelihood of rejecting it. Let's look at if we had 2 failures. Okay, now that's where you reject it. The upper bound for that one is 41%. Whoa, that's a lot higher than 4%. So we just kind of get fooled, because what we're doing is we're protecting against, again, the supplier. So the consumer for this overall decision-making process is really taking the hit on the sample size, because 13 is not very many samples to test for a failure rate of 4 in 100. So that's just what happens with AQL, but people don't realize what the implication of that. Now, reality, instead of doing an AQL, I like to look at this with using a 30,000 foot level charting approach. So in other words, we're not just looking at each sample to make a decision on if it's good or bad. What we're doing is to make a decision about the process. So that's really kind of getting into more of a quality assurance type role. Okay, let's look at this one here. Okay, let's move on here, I guess. There's a lot of, now we're getting to quality assurance, there's a lot involved with the quality assurance that goes beyond the P to MAG process. You know, you've got audits, you got ISO 9000 type audits. So what you're looking at there is basically getting into procedural checks. So do we actually go in and do this particular procedures? Also, we're saying, hey, let's look at inspection standard. Do we really go in and have calibration test as much as we should? That's kind of one thing we're looking at. And then, like I said, calibration procedures. So these are just audits and checking to make sure that we're doing the right thing. Now, but we still have some tools that really apply. We've got the control charts and the control plans, basically, are two things that can apply with the quality assurance role that you might have. So for business processes, we've been talking about and recommend the 30,000-foot level metrics in an early webinar, and this applies really to process control just fine. And there are cases where an X bar and R chart may be appropriate. However, to me, in my mind, they're very few and far between. The one case that can come to mind is if you want to go in and really control the subgroup variability between lots that you have, or between subgroup intervals, and you're really working to control that. That is one instant I can think of it applies, but 99.9% of the time, in my mind, you don't end up using it. So I end up using an individual's chart a vast majority of the time. Now, in this case, what we're really doing is trying to go in and separate common and special cause variability. Now, we're looking at common and special cause relative to Deming's philosophy as opposed to Schuart. You know, Schuart in the 20s, he identified an out-of-control signal as basically an assignable cause. Okay, well, we're looking at, you might have an assignable cause that's really common cause. So if we've got a differences between shifts or operators or machines or people or so on, those could be considered assignable causes. But and most people in the classes, when I poll them, they agree that those are typically considered common cause variability relative to a big picture of the overall process. So that's kind of what we view in the 30,000-foot level approach, just to kind of reiterate what we've done in previous sessions. Now, the P to MAG control plans are intended, can be used as a management plan for the process. So, as part of these plans, they include actions what to do when things go awry. So if things are not going well, hey, should I turn this knob? Should I put a red flag out there? What should I actually do when things don't go well? So we can go in and have those as part of the overall quality assurance plan. So I think that there's some techniques that are out there that we look at in the control plan on the P to MAG process that are applicable here. Okay, well, this is basically what we covered in this session here. We looked at the difference between quality assurance and quality control. We also talked about the P to MAG tools relative to quality assurance and also quality control. So if you got some questions here or a particular situation that you run across, I appreciate you sharing it with me, and we'll talk about it here. Got some questions here? No questions.
You referenced the P to MAG a lot, so where would you find the full P to MAG roadmap, if you will?
Okay. The P to MAG roadmap is in volume 3. So of the textbook is like 1,200 pages. It walks step by step through the project to MAG system. So I break down, I call it project to MAG, or I got an enterprise to MAG. An enterprise to make is volume 2, which looks at the overall business system. But in project to make, it's dealing with the define, measure, analyze, approve, control, but it's also got some additional drill downs in the measure phase. So volume 3 walks step by step through that overall roadmap and gets into all the nuts and bolts of it. In addition, now we've got a project execution guide, which acts as somewhat of a memory jogger for not only the tools, but how all the tools fit together. Now, it's not exactly pocket size, it's 8.5 by 11, but it follows a very good step-by-step process of getting through the overall roadmap of the make, and it's got decision trees and so on which tool to use at the right case or at the right particular situations. Now, the project execution guide also makes references to volume 3, and it also makes references to Minitab syntax, so that can help you actually take on and execute some of the tools within the overall roadmap.
Another comment is that I agree that using CP and CPK is confusing or can cause confusion when trying to explain it to the client. And training is key to the process. So just some feedback from other participants that agree on that topic.
Yeah, I think it's, yeah, I'm glad that you agree. Sometimes it's more difficult to explain it to others, but I've written some articles on that and also in the books that they can give you a little bit of an ammunition. Because even if your customer is asking for CP and CPK, you can train your customer. A company that's really good at Southwest Airlines, I think it's rather amusing. Every time I take Southwest Airlines, and they've trained us to stand up there and not complain, when you're boarding the airplane. So customers can be trained when it's sometimes the best thing for them. So I'm glad that you see the benefit of not using CP and CPKs.
We have a couple more minutes, so if there's any questions, please feel free to enter them. Also, if anything should come up after the end of this webinar, if you watch a recording, we would be happy to connect with you offline. So feel free to let us know any questions you might have. Okay, I haven't gotten any more questions, so we will see you again in 2 weeks for the 8th part of our series, and we will wrap it up with risk mitigation. So thanks for participating. Bye-bye.